Hello and welcome back. Now we are going to learn a little bit about the second bit of the bivariate data analysis. Remember, in our previous module, we learned that if you have two variables, how you're going to work with them. So we first learned that there could be many different types of variables. For example, a continuous variable, a categorical variable, could be ordinal variable, it could be variables such as interval level variables, ratio level variables, etc. In the previous module, we learned that if both the variables are continuous, which means if the outcome variable is a continuous variable, if the predictor variable, or what is often referred to as the explanatory variable, is a continuous variable, there are certain things that you can do. For example, you can plot a scatter plot, or you can work in some other ways. This time, we're going to learn if these variables are not of the same type. So which means if you've got a continuous variable as your outcome variable, if you've got a categorical variable for your explanatory variable, there are certain things that you can do. And for example, you can plot box plots for this. Or if both the variable are categorical variables, then you can do what is known as a contingency table. And you need to analyze them as well. So in this particular module, we're going to learn some of those issues. We're going to lay out the plans of the different types of variables, learn about box plots, and learn about contingency table, etc., etc. So without spending much more words, let's get started and roll our sleeves up and do some work. Thank you.
Hello and welcome to this particular edition of ePathshala. In the previous module, we had learned that the basics of taking two variables at a time. So we learned that variables can be continuous or categorical, and depending on whether a variable is continuous or a categorical variable, we can then set up our routines to do specific procedures and specific ways of graphically or visualizing their relationships. So we learned, for example, about using box plots, using regression lines, starting with some simple regressions, etc. We will be continuing much of this in our subsequent modules as well, but this first steps at the bivariate data analysis kind of sets up the steps for what we can do. And of course, we will be doing a number of different things because these set up the motives for more complicated data analysis. So it is important that we pay attention to this at this stage. And as you know, we have been following this motive throughout this series. That is, we introduce the basic concepts to some extent, lay out or describe the principles of the main point. For example, in this particular case, bivariate data analysis, what are some of the principles that we should be following, some preliminaries. We run a few demonstrations, and as we run the demonstrations, we tell you about it, and then we summarize the whole thing. The most important thing that we would like to really focus here is this, that this particular series is focused on R. So it's just one statistical programming environment in which we are showing you some of the things that you can accomplish with the R software. And of course, there are much more details that we have not chosen to elaborate here, which I hope that you will be learning and doing some additional studies. You can find many of those additional resources listed in the resources document that goes with this particular module. So I encourage you to go and read some of these things to get a sense of what the more detailed details of it. There are plenty of other books, manuals, monographs, demonstrations, programs that are available on the World Wide Web, and I would encourage you to look and go through them. So in this particular module, our objective is that we continue with the graphical exploration that we started with the bivariate data analysis part 1. This time we start looking at the continuous and categorical variables, and we'll learn a bit about analysis of variance, particularly with continuous versus categorical, and we shall learn about chi-square tests. In general, the motive goes like this, that anytime you come across a data analysis routine, it is very important that you understand the context of that data analysis. In other words, let's say you are interested to investigate length of stay of patients in a hospital with respect to particular changes in practices or general surgical procedures, some other things. Then you need to understand the context or the background in which such analysis are going to take place. So what is the variable? What variable is likely to be the most important variable of interest? This in turn will determine your data analysis as well. Because if you take everything out of the context, then you may get a set of estimates and perhaps even interesting results, but those results cannot be really translated back into the context where or which generated the data. Therefore, one of the things that I'd always encourage you as you start going through these procedures using the R software is try to keep in mind the context from where your data arose and the context in which the data analysis exercises are taking place. So, for example, there are some variables that can be both categorical as well as continuous. So you can interchange between a categorical and a continuous data. So in this particular example, we'll take a look at a continuous categorical data pair. Now you know that when your outcome variable is a continuous variable and your explanatory variable is a categorical variable, or vice versa, which means that if your outcome variable is a categorical variable and your explanatory variable is a continuous variable, in either case, you can construct box plots. And as we all know, box plots have got some very interesting properties. In a singular box plot, which is quite suitable for a continuous variable, you can take a look at the lowest value, which is going to be the lowest cutoff value beyond which if a value point lies, then that is labeled as an outlier. You can get the 25th percentile, which is the value which demarcates the lowest 25% from the remainder 75% of the values. You get the median, which is the exact midpoint, 50th percentile. You get the 75th percentile. And then you get the maximum range that will be defined by a value which is roughly around 1.5 times the interquartile range from the median point. So these features are pretty well known. And therefore, box plots are also known as box and whisker plots because they look like boxes and like two whiskers that extend out of the two surfaces of the box. So far, so good. Box plots are quite useful in the sense that it gives you a very nice, immediately available graphical summary of a continuous variable. Therefore, it is quite intuitive that if you could break that continuous variable into two sets so that for each set, not just two sets, but two or more than two sets, but for each set you could construct a separate box plot that would enable you to take in one instant, in one fell swoop as it is, a good idea about what is the distribution of the various points in terms of their outlier points, in terms of their median, in terms of their containment of the values. Where do they lie on that spectrum of the different cutoff that you have decided? It could be cutoffs. If you have got another continuous variable, you could actually use them as cutoffs. If you've got a categorical variable with two or more than two categories, it could be just that category for which you can plot the boxes for the corresponding continuous variable. Box plots in R are rather easy to construct. So in this particular exercise, we are going to load the package called PIMA, or rather the package called Faraway, which was written by Julian Faraway, who's a very renowned statistician, who's a great R guru. And then you load Julian Faraway's library. So it's called library Faraway. You could also write a require Faraway. In the third line, we decided to load the dataset PIMA out of Julian Faraway's dataset. There are PIMA is a dataset where Faraway was looking at blood glucose level amongst the Pima Indians. There are particular ethnical subsets, ethnical group in America. So he was going to look at the at some of the data on glucose metabolism, Pima Indians. Now we in this particular case are quite interested to see whether what kind of test results people have, and what do the test results mean? The test results are for glucose concentration. It's a very obvious, probably trivial example. But the beauty of R is this, that R kind of senses what variables you give it, and then based on the variable that you will provide R will automatically, or some people, as I say, automagically, will return you the correct plot. So the code is again very simple. We'll run through the code and we'll run through the parameters that are present in the code, or options that are present in the code. For box plot, the code is this. Box plot, you open a parenthesis, then you type the name of the dataset. I say in this particular case it is Pima. Then put a dollar sign, and then put or write the name of the particular variable. The dollar sign is important. Think of the dataset as a box, and within the box you have got all of these other objects, which is the variable. In this particular case we are talking about glucose, and we are talking about the test as two variables, and a box is Pima. So in order to abstract or extract the particular variable from the box, you use the identifier, the dollar sign, and then you separate your outcome variable. You write the outcome variable first, and then you write your explanatory variable next. The outcome variable is a continuous variable, so that gets written first. The explanatory variable is a categorical variable, particularly and only for box plots, so that's written next. And then you specify the title of the box plot. In this particular case, it is glucose levels for different tests. You label the x-axis, which is test results, and you label the y-axis, which is glucose tests. And as a result of this, you find that there are two boxes that are stacked, one after the other, the negative versus positive, because R in general follows an alphabetical order in which it kind of lays out the visuals. So for negative you get a box plot, for positive you get another box plot. And you can see that in this particular box plot, going by this, the positive test results are, they do not overlap. They should not overlap, as a matter of fact, but they don't overlap. And there is a considerably high value for glucose levels for people who had test positive results that returned as tests, where the test was positive, versus for those people for whom the test was negative, you see a lower glucose level. That's very, very obvious. So this is one example in which, or one instance in which you can measure the categorical, or you can observe or visually inspect the combinations of continuous versus categorical pairs. In the next bit, we are going to take a look at the categorical continuous pairs using what is known as a t-test. And t-test was of course, as you know, that there's a whole history to this, how t-tests were, came into being. We are not going into that history because that's not relevant for our topic today. But once again, if we could take the same pairs of variables, like glucose versus test, from Julian Faraway's Faraway package, looking at Pima dataset, all we have to do is issue a command that is t.test, then Pima glucose tilde Pima test. Now this particular t-test is one in which we just talked about two different sets of people, right? So these are unpaired t-tests, and you don't have to specify anything. You can, if you want, add some more parameters to this, which is, for example, you can specify whether you want a pairwise t-test or an unpaired t-test, and so accordingly you'll have to specify what kind of test you want out of this. So this is one way in which you can do some analysis for those situations where you have got a continuous variable as an outcome, a categorical variable as an explanatory variable, and then you want to make a measurement. The categorical variable in this particular situation had only two categories or two levels. And the way to do that is that for a visual inspection, you use box plots for more statistically oriented. In order to find out whether there was a change, you use what is known as you use t-tests. So here, for example, the mean for those who tested positive, the mean glucose level was 142.3, and for those who tested negative, the mean glucose level was 110.6. And you can see that that difference, the mean difference that they had, which is roughly around 32, that they had it ranged between minus 35 and minus 27. So that makes sense. And you can see that the p-value is very, very strongly suggestive that that difference was real. And we see that there was a number of, you can read off the t statistic, you can read off the degrees of freedom, and you can read off from these tables. It's very, very intuitive in that sense. Next, we are going to take a look at the pair, again, continuous categorical pairs, in which the continuous variable is in the outcome variable, in the outcome space. Categorical variable is in the x-axis or as an explanatory variable. But this time, our categorical variable has got more than two levels. So this time, what we have done is we have divided the age into three groups. That is less than 21, between 21 and 32, and more than 33. And what we're trying to do here is, again, we are taking a look at their glucose levels, but this time we are going to see what were the glucose level based on their age, age in years. And here you get to see that once more people, the older people, or the older participants in the study, they had higher glucose levels. Let me explain line by line what I meant by this. This is important here. And this is this, that here in the first stage, there was no categorical variable by age. So age was originally coded as a continuous variable, but for the sake of our analysis, we decided to convert it into a categorical variable, and we named that categorical variable as agerec. Therefore, in order to introduce a categorical variable in the PIMA dataset, we created a variable called agerec, and we assigned that variable to the PIMA dataset. The way to do that was that we specified that PIMA is the PIMA dataset, then put a $sign, and next to the $sign we added the variable agerec. So that would actually put agerec as a column in the PIMA dataset. Then we selected a function which is known as cut. Now cut is a function which you will use in order to convert a continuous variable into a categorical variable. This is an artificial example. What we are doing here is this, that we have taken a particular continuous variable and we have forced it to become a categorical variable. And what the marks of this categorical variable could be is entirely arbitrary, but you can again use a number of different things depending on, again, the context in which your analysis is going to arise. Here we decided that it would be meaningful for us if we were going to take, if we were going to, if once we had seen what was the range of the values, we could break it up into like three groups. So we thought maybe one point would be less than 21 years, one would be between 21 and 33, the other would be greater than 33. So what we did was that we broke it up, and therefore we used the term breaks, and we said 0, 21, 33, and a max of the age that we got. We could also replace 0 with like min of age and then could select it, but we instead chose to do it like 0. And the max could be 82. We found out already that the maximum value was 82, so we just stopped there. Then if you go back and then label them as such, That's what we have done. We have labeled it like levels PIMA age rec, and then we put expressions like C less than 21, 21 to 33, 33 and above. So that there are no overlapping age that group that we get to see. Next, what we do is this, that we plot glucose. So we this time when we do this, we have decided that all right, we'll do it slightly differently. In the past, you've seen previously we have seen that we use the data first and then the data object first, and we put a $sign and then we put the name of the variable and then we ran these. In this iteration, we decided, or we chose, that rather than doing it like this, we'll put the name of the variables first and then we'll specify or assign the data. So we say the variable is age. Again, the order of the variable matters, right? So the order of the variable in this particular case is that we put the continuous variable first, and then we put the categorical variable next. So the continuous variable is glucose, we put it first. We put the categorical variable age rec next, then we specify the data. And then all the other bells and whistles. That is, the title is given with the option main, and then we write glucose levels with age in years. We specify the Y label, and this is glucose levels. We specify the X level, X-axis, which is age in years. Note that it does not matter in what order you put the main, in other words, the title for this, the label for the Y-axis, that is YLab, or the label for X-axis, the XLab. They can go in any order. The only thing that matters as far as order is concerned is that you put the continuous variable first, then the categorical variable, in order to get the box plots. Then if you take a look at the box plot, which is present on the right hand side, you can see that the on average for people who were 33 years or older, for them the glucose level was higher. Okay, so this is one way in which you can analyze things. In the next, we are going to take a look at what happens when we have got pairs of categorical variables. So we have got a categorical variable and another categorical variable, right? So let's take a look at this. In this particular case, we are going to take a look at a pair of categorical versus categorical variables. We are still in the context of discussing what is known as a bivariate data analysis. So in other words, we've got two variables. One variable is continuous. I mean, one variable is an outcome variable. The other variable is an explanatory variable. So we construct a table. By convention, your outcome variable by convention, your outcome variable, the levels of your outcome variable will go in columns. And the levels of your explanatory variable will go in the rows. So that's now rule number one. Number two, when you have got an outcome variable and an explanatory variable, both of them are categorical, then by default, you will develop what is known as a contingency table. In a contingency table, it can take any shape from a 2x2 table in which you've got only two categories of your outcome variable and two categories of your explanatory variable, to any number of cells that can go into this. So n by n. So it could be like 20 levels of your categorical variable for the outcome variable and 20 levels of your explanatory variable category. So you've got a table which has got 400 cells and beyond. Okay, but the motif is the same. You actually put the continuous variable in the form of columns. The explanatory variables always go in the form of in the rows. Again, here as well, what we've done is we have decided to pitch test against age rec. So we wanted to see whether people, who tested positive, whether they were more likely to be what would be their age breakup? Like, are they likely to be more older people of the cohort, more likely to be testing positive or not? So in order to do that, we again issued a command, and this command, let me walk you again line by line. The function for this is table. So table is an inbuilt function in the package stats of R, which loads automatically when R loads. You don't have to have a special package for this. So in that function table wants you to put it in a way, and again here the order in which you put your variables matter. For example, for table, it's a little bit like the plot variable, right? So your explanatory variable goes first, followed by your outcome variable. In this case, our explanatory variable is age, right, recoded, and our outcome variable is the test results, positive or negative. So table, then we source the dataset name, which is PIMA, then we add a dollar sign so that we extract the particular object that we want, or the particular variable that we want from the object, which is a data frame called PIMA. In this particular case, it is agerec. Then we put the next variable, which is again PIMA, then a dollar sign, and this time we want it to be test, and that's it. If you do not give table any other parameter, or table in this form just puts out the contingency tables in the form of raw numbers. If you have to add additional details to it, you can save the table into an object, and from that object you extract other things that you need. For example, you can get a sense of the percentages, or you can extract the row percentages, or you can extract column percentages, and so on and so forth. I encourage you to look into the table help files to learn a little bit more on that particular function. For us, we are happy that we're only going to put together the age test, which is the object in which we kind of saved the table, and we can manipulate the age test object in order to get every other details out of the table that we would like. But in this case, we were happy just to put out the table, and you can see that there seems to be some sort of a pattern when it comes to positive tests. You can see that only 5 people had who were less than 21 years tested positive for the glucose, which of course was very, very high. I mean, positive for kind of diabetes or whatever that was. And more than about 146 people, age group 33 years or older, tested positive for the glucose test in the PIMA-Indian group that we were looking at. So it immediately gives you a sense that there may be an age involvement in it, but how do we characterize this better? So in the next bit, we take a look at the same categorical pairs, but this time we would like to take a look at the statistical properties of that kind of a table. So in table, we were able to tabulate or construct or set up a contingency table with the numbers there, but what do the numbers tell us? And this is where we start talking about putting together a chi-square test. Very simple. The chi-square test again belongs to the same thing, except the results of the chi-square test can be saved in an object. In this particular case, we have tested it in an object. We have stored it in an object called chi-test age test, and then we issued the function chi-square dot test. This is the name of the function. This function is loaded in the stats package of R, and then you can see that we can extract from there the p-values. So again, we use the object in order to extract whatever that we want. And as you can see, R is reticent. It will not give you copious outputs. You will have to ask for it. In this case, we were interested in the statistic, and we were interested in the p-values. And you can see that we can specify the number of decimals that we want. So for example, for p-value, we wanted 4 places to the decimal. For the statistic, we wanted 3 spaces. And you can see that the chi-squared statistic is 55.839, and the p-value is less than 0.001, because even at 4 places to the decimal, it still returned a 0. Okay? So this is how we work as far as this is concerned. In the next, when we do something like this, it is very important that we would have a visual inspection. Now, normally we would have the visual inspection go first and then this, but in this particular case, we wanted to reverse the order to a little bit. So we said that we'll do a bar plot of only that bit that talked about the positive. So look at the codes again. Remember that we saved the table into an object called age test. And because it was a table, we wanted to find out the dimensions of the table. So we use the function dim, dim, and it tells us that they've got 3 rows and 2 columns. So it'll point out that. So because there are 2 columns, and because we know that R actually saves everything alphabetically, therefore the second column is going to be the one that talked about the positive column. So then we decide to bar plot it. And remember that in bar plot, we actually put in either a summary or a table object. So in this particular case, the table object is age test. And then we extract from the table object the subset of the second column, which is column number 2. And therefore, we put square brackets, then put a comma, and then put the number of column that we want to extract out of it. And then we put the regular options there, the main or the title of the table, etc., etc. Okay. So so that's one way of doing these things. But this time, what we have done basically is we have picked up the raw numbers. But if you were a little bit more discrete, you'd be more interested to find out the percentages rather than the raw numbers. And here it gives us a sense as to we can extract the row percentages of this. Okay, this is more topical for us. So we said, give me the row percentages, and therefore we use another function called prop.table, and then within the table object, we specify that we want row, and the symbol for row is 1, or the indicator of the row is for 1. The indicator for the row our columns are 2. So if we wanted column percentages, we would have put like age test, comma 2. But in this particular case, we're interested to have the row percentage. So we'll say 1. And then we multiply it by 100 because rather than proportions, we want percentages. And then we round it off to 2 places of the decimal. And then we put this, because it then stores everything into, again, another object, which is called age test PCT, and then we subset that object as before with the second column, and we put it out there. So here is the result of that graph, and as you can see that there is a corresponding high increase in the percentages for people with who were 33 years or older than that. If you do the same thing but with just numbers, you see that again there is an increase, but note the difference. That increment is not that much. So therefore, it is advised that when you put, when you visualize, inspect contingency tables, use the percentage option rather than the raw numbers, because raw numbers may not always give you the correct kind of impression, or may not give you the good visual impression that you get then further use. So to summarize, in this particular module, which kind of concludes our initial inspection of the bivariate data analysis, and will continue with this, but in a slightly different direction now. We talked about we finished or completed the basic concept of bivariate analysis. We learned that it is predicated by the types of the outcome and the explanatory variables. We learned several ways in which you can inspect visually the 2 dimensions, or the 2 different types of variables, and what can we do about it. Okay. In the next, we're going to continue this example and start learning about regressions and linear models, etc., etc. Thank you very much for your attention.
Welcome back. We just covered bivariate data analysis part 2. So at the end of completion of part 1 of bivariate data analysis, where we were looking at the different kinds of variables, and if the variables were like both continuous, what you'd like to do. And then in part 2, where we focused on the continuous and the discrete cases, and we found out about doing box plots, we found out about setting up contingency tables. You should be in a better position now if you start with two different variables, what strategies you can adopt to analyze them. So I leave you in this module with this knowledge. We are going to pick up on the same topics in the second bit, where we're going to learn about regression. Okay, so till then, bye bye and keep learning. Thanks.